Hello, everyone. I'm very happy to welcome Professor Adam Sheffer to give us a talk on geometric incidences. And so without further ado, Adam, I'll let you start.
Thank you. Thank you for having me here. I'm always happy to visit this program. Let me start sharing. So, hi everyone, I'm Adam. All right. So what we're going to do today is talk about a mathematical research front. That is an area of mathematics that mathematicians are currently working on. They have very hard problems that people have been struggling with for decades, world-leading mathematicians. Most of these problems, most of the research front, I would say, are not that accessible. It's hard to explain them in a brief talk like this. Some of them you need years to study what they mean. But we're going to see a mathematical research front that's relatively easy to understand, that you can understand more or less in such a brief talk, even though these are very difficult problems. Just to get some impression what's happening in math, I guess, in the math world now. I don't want to be the only one speaking in a sense. So please, whenever you want, I'm happy to get any questions. Oh, are we using the chat here? Yes, I'm happy to have get any questions, comments, jokes, whatever you want, okay? Participate as much as you want. I'll try to ask you also questions. So let's start. We are going to talk about an object called geometric incidences. What is that? So imagine that we're in the plane. Oh, you know what? Let me say one more thing before I actually get into the math. Especially if something is not clear, even if you think it's a basic thing, please ask me to clarify it. You'll probably be doing a favor to a lot of people. I don't want to just talk and have everyone losing me. So whenever you're not sure about someone, please ask me about it. I'm happy to clarify, give examples, whatever. All right, so we're going to talk about geometric incidences. Imagine that we're in the plane. We have some points in the plane. We have some lines in the plane. An incidence is a pair of one point and one line. Formally, this is a pair in math, 1 point, 1 line, such that the point is on the line. For example, here on the left, you can see one incidence. There's a 1 point, 1 line, and they form one incidence. What do you think? How many incidences do we have here in the middle case? How many incidences do we have here? Can you write to me in the chat? Very, very good, people. Thank you. The important thing here, we have two incidences because this point forms an incidence with this line, and this point also forms an incidence with the same line. It doesn't matter that it's the same line. It's a different pair because the point is different. Okay, and here on the right, how many incidences do we have here? What do you think? Good. See all sorts of answer. So it's not about, the important thing is not to be about being right here. It's just to make sure that this makes sense too, because we're going to keep talking. We're going to get more deeply into this. So we do have 6 here. Why is the answer 6? Because this point forms 2 incidences. It's on 2 lines. This point forms 2 incidences. It's on 2 lines. And the same here. So 2 plus 2 plus 2, that's 6. Is that okay? If this is not clear why we have 6, let me know. It's important that we have the basics right. Each point forms 2 incidences, so it's 6. Okay? All right, let's do one last check that you're with me. Again, it's not really about getting the right answer. It's just want to make sure that this is clear. Here's a bigger example. Take a moment and tell me how many incidences you think we have here. Wow, everyone seems to have the same opinion on this one. Okay. Thank you for answering. I appreciate it. And you are all correct. We do have 15 incidences here. Why is that? So we have 3 incidences here, and 3 here, and 4 here, and 2 here, sorry, 3 here and 2 here. So that sums up hopefully to 15, unless we were all wrong. Okay, so these are incidences. Now, my goal today is to talk about what currently is being done with incidences, but I kind of wanted to start with something more historical. So let's go back a bit to the 19th century. So people started in some sense looking at incidence problems in the 19th century. For example, there was a famous mathematician in the 19th century called Sylvester. When you study math in college, you tend to study a lot of things he came up with. And beyond just coming up with a lot of good math, he also named a lot of mathematical objects. For example, he coined the term matrix and graph and discriminant, all sorts of other things. And one of the things he did is he started looking at incidence problem. I'm going to show you what his problems are in a second. And I only know one case before him. And this is a weird case, also from the 19th century. There's a book. This is a book from the 1821. Rational Amusement for Winter Evenings, a collection of 200 curious and interesting puzzles and paradoxes. It's a pretty long name. It keeps going for a while. It's a mathematical riddles book. And it had about 10 incidence problems. I want to show you one. And I'm going to guess that probably no one will have any idea what this question is trying to say just because it's from 200 years ago. Let's look at this problem. Here's one of the incidence problems. Fain would I plant a grove in rows, but how must I its form compose? With 3 trees in each row, to have as many rows as trees. Now tell me, artists, if you please, 'tis all I want to know. What is this? Is this really a mathematical question? Anyone thinks they know what this might be talking about? Any guesses? Pretty unclear, right? So let me try to write it in present. Very good. Yeah, very good. You have some good ideas here. Very nice. So here is how to briefly say it in present day English. You want to place x points in the plane. They don't tell you how many. They just tell you, can you place some number of x of points in the plane such that at least x lines contain 3 of the points. So they do it they phrase it nicely, better than I can, with planting trees in rows. So here's a bad example. This is a failed attempt to do this. So here we have 9 points in the plane, 7 points in the plane. And if you count, you'll see that there are only 6 lines that contain 3 points. Okay, do you understand the problem? Is the problem clear? We want to put some number of points. So should we have at least as many lines that contain 3 points? Here there's few, as the number of lines is smaller, so this is wrong. What do you think? Want to try to play with it? Want to suggest something? How can we try maybe to do that? Or what can we try to do? So I see so we have a suggestion 9. Do you mean putting 9 points? How would you put them? If you want, you're even welcome to use, if that's allowed here, you're welcome to use the annotate function option and write on my slide here. What do you think? How can we try something?
I was just saying 9 points.
Sorry? It's just saying 9 points.
I was just saying 9.
Okay, yes. So the question is, how do we place those 9 points, right? Good. How can I try to place 9 points so that I have at least 9 lines that contain it? So I see someone is trying to put 7 on top. I I don't see n. So you need 3 points on each line, right? At least 3 points on each line. 2 is not enough. I think that when you try to put 9, maybe the first thing you're going to try is something like this, putting them kind of in a lot. Imagine that I drew it nicely. You're going to try to put it something like that, right? So I have 3 horizontal lines and 3 vertical lines. How many lines with 3 points do I have here? Can you tell me? 8. Very good. Thank you. Imagine that I drew this straight. Okay, I'm not so good at drawing. So we have 8 of those. So that's not good enough, right? We still didn't get it. If we use 9 points, we needed to have at least 9 lines. And that's a hard problem. I'm not, don't feel bad if you don't have any idea. It's a hard problem to solve. So let me try to give you a hint. I wonder if that would work. You know how in you study geometry in school, and there are a lot of this Euclidean geometry comes from ancient Greece or other ancient civilizations, and you have all sorts of Pythagorean theorem and Thales theorem and stuff like that. There is a lesser known theorem from these ancient Greeks that I'm going to guess that most of you don't know, but some might, that easily solves this. Anyone have any thought what is a very old geometric theorem might solve this problem? As I said, I'm guessing most of you don't know it, but some might. All right. So let's, wow, I got the right answer, but in a private message. You should write it to everyone. Yes, thank you. Joseph here gave us the right answer. What is this theorem? So here's briefly this theorem, Papu's theorem. You take a line, any line that you like, and you put 3 points on it. Let's call them capital A, capital B, capital C. And then you take another line, and you put another 3 points on it. Let's call them lowercase a, lowercase b, lowercase c. Any lines that you want, any 3 points that you want on them. Then you take the intersection points the way they're drawn here. I didn't write it because it's too long. So you look at the line between capital A and B. You look at the line between capital B and A, and they intersect, and you call that intersection point X. And you do the same, capital A and C, intersect capital C and A, you call this Y. And capital A and C, capital C and A. Okay, so what the theorem says is if you start with 2 sets of points on 2 lines, this intersection point will always be on a 3rd line. X, Y, and Z, the intersection points will always be on a line. Okay? And that's exactly what we need. Is it why? Why does this solve our problem? Can you tell me? How many points? Yes, very good. Thank you. So how many points do we have here? We have 9, right? How many lines do we have here that contain 3 of the points? How many lines here contain 3 of our points? Can you tell me? 9. Thank you. We have, right. Thank you, everyone. Some people sending me private messages. I appreciate it if you just do it in the general chat if you're willing to. Thank you. So we have 9 points and 9 lines. So I'm guessing that this is the solution that the book intended. That's probably what at least my guess, that's the solution they had in mind. If you move back to the present and you use the math that we have now, we can completely crush this problem and do much better. I'm going to say it very briefly and not accurately, just to say, give you a vague idea, but it's not, I'm not going to tell you the technicalities. So you probably know well quadratic curves, curves of degree 2, parabola and a circle and stuff like that. They're all defined by equations where each term is of degree 2. Cubic curves are curves that have degree 3. Here you have 5 examples here. For example, this curve defined by y squared equal x cubed. Here, this curve is another equation with degree 3 when you open the parentheses. So these are cubic curves, okay? There's something we know today that basically you can take n points on a cubic curve and get about n squared over 6 lines that contain 3 points. So I stole this drawing from somewhere, and I actually need the blue lines. It's easy to see the red lines actually need the blue lines. We took here a cubic curve of degree 3, and we placed some points on it, and we have a lot of line passing through 3 points, the blue lines. Now, this is much better than the question asks you. Imagine that n is 1,000. So you have 1,000 points and a 6-digit number of lines. That's so many more lines than points. It really crushes the problem. So it's much, much better. The number of lines is so much larger than the number of points. This relates to something that's called group theory. If you're a math major in college, you'll study group theory. There's something called a group here that does it. Doesn't matter. Anyway, so this was some 19th century math. Let's get closer to the present. Let's move to the 20th century, I guess. I want to remind you, if you have any questions or comments or whatever, just stop me, okay? I like being interrupted. You're always welcome to. Okay, so what we're doing now is we don't really care about 9 points and 9 lines. We want to have a lot of points and a lot of lines. So imagine that we have m points and n lines, and these are huge, huge, gigantic numbers. Too large to draw properly, too large to have any effect, that any phenomena that only happens with small examples. This approach, I don't want to say too much about this. This approach comes from originally from the analysis of algorithms in computer science, where people don't really care if an algorithm is efficient when the input is small. And these days, you know, you have big data, all of that. We care mainly what happens when there are very big numbers. And it's gradually taking parts of math also, this approach. So we say m and n are asymptotically large. You just imagine that they're huge, too large to imagine or to look at small examples. All right. So now we have a lot of lines and a lot of points. So we have a lot of lines, a lot of points. We want to have many incidences, okay? So forget about lines with 3 points. We don't care now about lines with 3 points. In fact, to have a lot of incidences, you want to take lines that have a lot more than 3 points. I want the lines with a lot of points. So what I'm asking you now, can you guess, suggest ideas, if I need to arrange a lot of points and a lot of lines, and my goal is to have a lot of incidences, what can I try? Let's focus on the point set. How can I arrange a point set of a huge number of points so that maybe I can have a lot of lines with many incidences? Any thoughts, suggestions? You understand the problem? You can take your time, not in a rush. What might be a nice way to arrange many points so that you can put lines that form many incidences? I'm just asking for a guess. It's a very hard problem. You're not expected to completely solve it now in any way. No thoughts? Oh. So there's no more than 2 points. Someone asked me in private, do I want no more than 2 points to be collinear? No. You need a lot of points. You need a lot of points. To be on the same line. If every line just contains 2 or 3 points, you won't be able to get many incidences. So we want something much larger than that. So how can we arrange points that there are many, many lines that contain many points each? So I'm only getting private messages. Are we only allowing private messages? No, I just don't want to share with everyone. Right, so people are suggesting to me, we want to have a lot of points that each point have a lot of lines through it. Agreed. How can I do this? Any thoughts? What form can we arrange a set of points so there are many, so we can form any incidence? No thoughts? Okay, so let me give you an example. Let's use a lattice. What do I mean by a lattice? So something that looks like the picture here. Ignore the lines for now, just the points. I wrote it also in text here. Take m points such that these are all the points such that their x coordinate is an integer between 1 and square root of m, and their y coordinate is an integer between 1 and square root of m. So that gives us about m points that look something like that. It's a lattice. Do you understand what I mean here? Does it make sense? Please stop me if something is unclear. It's my job to explain, right? Okay. So as I said, so this was the person who looked at it first, as far as I know, is Erdős. He's a famous mathematician from the 20th century. And he tried to get to a lot of incidents. And he said, okay, let's think about it. This way, it seems like we can have a lot of lines that each line contains many points, right? There are a lot of lines here that contain many points. And the question is, how do we count that? The easy part is just taking horizontal and vertical lines, but that's not enough. We want a lot more lines. And he found a way to do it using something that's called Euler's tangent function. If you don't know what it is, doesn't matter. Another word that Sylvester coined. And with some calculation, he got to the number of incidences is some small constant times number of points to the 2/3, number of lines to the 2/3. Quite a weird expression, right? Somehow the number of incidences is about the number of points to the 2/3, number of lines to the 2/3. Now the constant is somewhat less important because m and n are huge. So the dependency in them is the main thing here. Multiplying it by a small constant, it matters, it changes something, but it's a lot, the change is much smaller than the dependency in m and n. And then Erdős asked, can we do better? Maybe there's a more clever way of placing the points such that we can have even more lines that contain many of the points. And math is hard, right? You don't know if you're going to try now for years to find such a configuration. Maybe it doesn't exist. Or maybe you can spend years trying to come up with a proof that says that you cannot do better, but maybe that's also wrong. So how do you know? Any guesses? What do you think? Do you think that this is the best we can do? Do you want me to, if this expression is not clear, let me know. I'm happy to repeat. Or otherwise, what do you think? Can we somehow maybe arrange the points more cleverly than Erdős and get more? Or is that the best? Any thoughts, guesses, comments? All right. So it's hard to say, I think. I hope that this is why you're not telling me anything, not because everyone stopped listening to me. Oh, I have someone asking, can I explain C again? Yes. So Erdős got that the number of incidences here is approximately the number of points to the 2/3, the number of lines to the 2/3, times some small constant. So you might want to think of C as 5 or 10 or something like that. Okay, it doesn't depend on the number of lines, doesn't depend on the number of points. It's just some small constant. Let's call it 10. And as I said, the reason we just write C here instead of the exact number is that we somewhat care less about this. This is going to be huge, m to the 2/3, n to the 2/3. This is small, so we care, in some sense, we care less about this. Okay, is that okay? Did I answer your question okay, or do you want more to talk about this constant more? Okay, thank you. So it turned out that you cannot really do better up to a constant. A while later, in 1983, Samarady and Trotter, two mathematicians, Prove that whenever you have m points and n lines, doesn't matter how you put them, the number of incidences is at most the number of points to the 2/3, number of lines to the 2/3, times some small constant, not the same constant. So you can imagine, if you like, that Erdős found a construction with, let's say, 10 times this, and maybe they proved that you cannot do more than 20 times this. Okay, so it's not exactly the same number, but it's the same, we call it the same order of magnitude, or the same asymptotic size. The dependency in m and n, it has to be m to the 2/3, n to the 2/3. Again. So the number of incidences between any set of endpoints and any set of n lines is at most some constant times number of points to the 2/3, number of lines to the 2/3. And there exist a specific sets of endpoints and n lines that form this number of incidences. So the problem is more or less solved. Oh, I like it. Very good comment on the chat. Yeah, it matters more how the result grows as a function of m and n than the constant. Exactly. If we were talking, if we had a talk that focuses on this topic, on asymptotic numbers or analysis of algorithm, I would show you examples why the constant matter less. But I guess this is too far from our topic today. But the example is, the message in the chat is perfect, right? Okay, so this problem is asymptotically solved up to the constant. Any set of endpoints has at most this number of endpoints and n lines has at most this number of incidences up to a constant, and you cannot do better. Is that okay? Keep asking if something is unclear. Okay, that's what this talk is for. We're going to see today how you can prove this even, but not quite yet. So this problem is solved almost 40 years ago, except for the constant. But I said I'm going to show you a research front that is still open and mathematicians are struggling with. So what's going on here? So this is just one incidence problem, maybe the simplest incidence problem, just points and lines in the plane. But there are many other incidence problems. So maybe I can get you to guess a bit. If I asked you, okay, let's say you already know how to solve this problem. We're going to see soon. What can you try next? What might be a variant, a different version of this problem that's a bit harder or a bit different? What else can you ask about numbers of incidences that we can try to solve next? Any thoughts? Well, yes, very good. Exactly. Also very good. So we can try many different things. There are many types of incidence problems. This is just the simplest one. And not only the simplest one, almost the only one that is solved. Almost all problems are still open. For example, you can ask, what is the maximum number of incidences between points and circles? Instead of lines, we have circles. Embarrassingly, even though the case of line is solved for almost 40 years, this is still wide open. We don't know what the maximum number of incidences between points and circles is, even though people have been trying. And you can try parabolas, other types of curves. You can go to higher dimensions, like Pascal suggested, the lines in 3 dimensions. We can try planes or spheres. By the way, since we have a good answer from Pascal here, maybe I'll mention the Papuch theorem that we saw, the ancient Greek theorem that we saw, is a special case of a more general theorem that's called Pascal's theorem. Anyway, so we can try, there are many other types of incidence problems here. This is really just the beginning. I don't want to start. You can deal with all sorts of more advanced mathematical versions of the problem. And almost all of these problems are still unsolved. We don't know how to solve them, even though people are working on them. And now you might say, great, Adam, you have 1 million incidence problems. Why do we care? Why would anyone want to try to solve now 1 million variants of incidence problems? And I would say, because there's a good question, a hypothetical person I'm pretending to speak to, but there are all sorts of answers, and I would like to present a few of those. So let's start with the most standard answer that I'm guessing that you're also gonna like the least. Mathematicians are excited about natural problems that are hard to solve. And this is a very natural question. It's just points and lines in the plane. Points on lines. And for some reason, it's very hard to solve these problems. So mathematicians like this kind of problems. And we can have a whole lecture about why this approach is good. Weirdly enough, history is full of examples of problems that no one thought would ever be useful for anything. Mathematicians still found exciting and turned out to be really important. Maybe one classical example out of many is there is something called non-Euclidean geometries. It's geometries that are curved, that they behave differently. When this started, everyone assumed that this will never be useful for anything, ever. And then it turned out to be exactly what Einstein needed for his theory of relativity. So because mathematicians still found this interesting and insisted on studying this, Einstein was able to do his general theory of relativity. And this is just one example. There's so many big, important examples of this happening. But let's say you're still not impressed. Let's say you're practical people, you're not satisfied by such an answer. What else can we say? Another answer. Incidence bounds are surprisingly useful for studying other problems. I don't have a good explanation for this. For some reason, problems from many different fields, you make progress on those by using incidence bounds, incidence results. Now, some of you were probably here in my talk last summer. Last summer, I talked about something completely different, some problem from number theory about sums and products of numbers. And the main progress, the main breakthrough in that topic was by using incidences. I briefly mentioned incidences there. We didn't really talk about them. If you want, this is recorded on YouTube. You can see how a problem that seems completely unrelated to geometry, it's about number theory, suddenly you have a huge breakthrough by looking at incidences, and there are many examples like this. And today I want to show you another one of those. But a geometric one, so maybe it's less surprising that you can use incidences. So let's do an example. Sorry, I just lost my chat. I want to make sure I have it. Okay, and keep using it, please. Here's a problem. We have n points in the plane. When you have n points, we want to look at triangles that these points form. So you can look at a figure here. I just have 5 points. These span all sorts of triangles. By that I mean there are a lot of triangles whose 3 vertices are from this set of points. If you have n points for some huge number n, you're going to have almost n cubed triangles. Every 3 points span a triangle, including triangles that are flat, kind of degenerate triangles, 3 points on the same line. So there's a problem that asks, just a small problem, out of these about n cubed triangles, how many can be right-angled triangles? Okay, so the question is, if I have n points, how many right triangles can they span before they have the vertices of? Let's start with an example. I put here 5 points. How many triangles? How many ways can I take 3 points out of 5? Do you know? Happen to know? If I have 5 points, how many triangles do these 5 points form, including the one that's completely flat? We're also going to call this a triangle. Is a nice idea, but not quite. 10. So I got very good. So those of you who know some basic combinatorics are telling me 5 choose 3, but it's completely fine if you don't know what that means. And it's 10, exactly. Thank you. So many good answers here. Thank you, people. 10. And so that's 10 triangles. Out of these triangles, the 10 triangles I have here, how many are right angle triangles? Can you tell me that? Very nice. I see 5 and I see 6, and both are correct in some sense. It depends how you imagine, what you imagine is happening here. It basically, the 5 or 6 depends if you imagine that this here is a right angle or not. So both answers are valid. I wrote 6, doesn't matter. 5 is just as good. Why is that? So we can count. We can count to the right. Actually, it's 6 or 7. Sorry, I think it's 6 or 7. You're right. Anyway, let's count. We can cut the square into 2 triangles with a diagonal, and that gives us 4 right angle triangles that are half of the square. And then the question is, how many right angle triangles use the rightmost point here? So there's this one. There's this right angle triangle using here. There's this one using these 2 points. So that's already 6. And I guess if you imagine that this is a right angle, then you can get 7. So it's 6 or 7. Sorry, you're right. Good thing I have you to correct me. All right. So the general question is not about 5 points. It's about huge number n points. And then there are about n cubed triangles. We want to ask how many can be right angled. So let me ask you this. What might be a nice way of placing a lot of points in the plane such that they form a large number of right angled triangles? How would you try to place points to get a lot of right angled triangles? Any guesses? I'm only asking for guesses, right? It really doesn't matter if you're right or wrong here. I'm just, in math, it's a hard field. When you try to do research, you do wrong answer all the time. Most of what you do is wrong answers. You just learn from them. So, okay, so someone suggested n-2. So you can tell me how you get n-2, or you can suggest other ways of placing n points in the planes to get, or specific ways. How would you place the points? How would you like to place your points to maybe get a lot of triangles? Just guesses, that's all I'm asking. So someone suggests to me in private, arrange them all in a circle so that a bunch of pairs lie opposite to each other. Nice. Yes, that's a nice way of doing this. What else can we try? Other thoughts? I want even more right angles than if you place them in a circle. Grid. Oh, very nice, very nice. Indeed. There are other ways. You're welcome to suggest other idea. Lattice grid, yes, exactly. That's one way of doing it. I put 2 examples here. You can maybe come up with more. So here's what you suggested. So if we have n points, it's square root of n rows, square root of n columns. Together you get about n points. Okay. Here's another option. Try to do an L shape. So 1 column with half an n points, 1 row with say a half an n plus 1 point. Okay, how many right angle triangles approximately do you have? Can you tell me how many right angle triangles approximately? We don't care about the constant, we just want an estimate. Approximately how many right angle triangles do you think one of these configuration has? The one you're more comfortable looking at. Okay, so let me help you. Let's do the lattice. Take any point. Let me draw something. Take any point here. Let's say I chose, this is my point, okay? How can I form a right angle triangle now with this nice point here? How can I get right angle with it? Right angle triangles with it? Nice, thank you. Yes, and more generally, what I can do is I can take 1 point from the same row. Very good, very good. 1 point from the same column. Doesn't matter which one. So I have about square root of n option of choosing a point from the column, about square root of n choices of choosing a point from the row. And each of those is going to give me a right angle triangle, right? Let me draw something. Let's say I chose this and I chose this. So I got a right angle triangle. Any choice of those will give me a right angle triangle. So for any point that I choose, yeah, you're giving me a harder one, kind of. Yeah. So maybe it depends really what is happening here. Maybe you can do that. So any choice of so any point that I start with, the one I circled in red, is next to the right angle for at least n points. There are n triangles. There are about n triangles I can form this way. So n triangles for each point. What can I say about the total number of triangles? Approximately how many would that be? Any point that I choose, I can find about n right angle triangles next to it. So in total, I get very good n squared. N times n, very good, is n squared. Very nice. Is that okay? Do you see what's happening here? If not, ask. I'm here to explain. If I'm going too fast, let me know. Good. So we can have about n squared up to some constant triangles here and also here. Because here you just take the corner, one other point from the column, one other point from the row. Again, that's about n squared over 4 ways of doing that. So good. We know that there are about n cubed triangles in total. We found a way of having about n squared right angle triangles. And now it becomes harder because maybe there's a nicer way. Maybe we can think harder and find a way to get even more right angle triangle in some other configuration, some other set of points. Or maybe not. How do we know? So let's try to get an upper bound. Let's try to say for any set of n points, you can never have more than some number of triangles. Let me clear this, what I put here. So here's my question to you. A bit harder question, I guess. Instead of asking to prove that the total number of right angle triangles is most something, let's start with a more local problem. We fixed 1 point, P, just 1 point for my point set. And then I want to know how many right angle triangles this point participates in, where it is not next to the right angle, it's next to an acute angle, okay? So I want my point, ask how many right angle triangles it's going to be next to, where it is not next to the right angle. You know what, maybe I should ask, Kovan, I think this is going towards me talking for about an hour and a half and then having half an hour for questions. Is that reasonable, or do you want me to make it a bit shorter?
No, that's fine.
Thank you. Okay, then let's aim for that. If you want, I can skip some stuff. Okay, so let's look at this example. Here's my point I fixed P. I want to ask how many right angle triangles it participates in, where P is not next to the right angle. Can you tell me what you think? Try to count how many right angles P is one of their vertices and not the vertex next to the right angle. Okay, you understand the question? So for example, let me do one example. You know what, let me give them all names. Let's call them A, B, C, D, E, F. Okay, so one triangle that I have, let me know if you don't see what I'm writing now, is PA, let's just write it like this. PAB is one right angle triangle that P is a vertex of, and it's not next to the right angle. What else? Give me more. I want to see more of those. PCB. Let's see. Yeah, PCB, very good. More. PCE, very good. Yes. What else? PDC, very good, very good. We have 4 already. Are there any more? PAC. Okay, so PAC is a triangle, right angle triangle. That's good. But we want P not to be next to the right angle, right? The goal is for P not to be next to the right angle, so we cannot use that one. PEF, yeah, if we imagine that there is indeed if we imagine that this is a right angle, then PEF is a good answer, yes. Anything else, or do you think we're done? I think we're, so PAB, yes, correct, we already have it. Good, thank you for the help. Now let's see if this is also the number I wrote here in the slide. 5, yes, okay. So assuming I was right before, we're also got the right number now. But we're not interested in such a small configuration. We're interested in, we have endpoints. We want to answer this question where there are endpoints, any endpoints, not just one example. So let's think about it. Let me see. Let's say that Q is the second point of our triangle that is next to the right angle. Okay, Q is next to the right angle. Where can the third point be? I want to have a right angle triangle using these 2 points and one other one, such that Q is the one next to the right angle. Where must I put the third point? Can you help me with that? You can even draw on the slide if you want an example of a point, or say something more general. I want a right angle triangle. Complete this. You have 2 vertices. I want the third one so that I get a right angle triangle. The right angle is next to Q. Where can I place the last point? Need help. On a circle with diameter PQ. That's a good idea. I think that would give me an isosceles triangle. If the question was for isosceles triangle, that would be the way to solve it. Now, oh, nice, nice. I got a good answer in private and another good answer in public. Very good, people. Very good. You got it very well. Exactly. The third point, which so many people pointed, some private, some public, has to be on this line, anywhere on this line. Put a point on that line. Let's put one just to see an example. If I put a point here, my third point here, I get a right angle triangle where the right angle is next to Q, or any other place on this line. If I put a point anywhere else, it would not work. It's exactly the points that are on this line. Do you see what? Do you see this? Does it make sense to you? Let me know if something is not clear. So I'm told to put it on the third point okay. So I have all sorts of other suggestions that suggest how to get a right angle triangle, but not when the right angle is next to Q. We want the right angle to be next to Q, okay? Specifically next to Q. Okay. So let's clear this. Let's try another example. Let's say now I put Q here. Where should I put the third point to get a right angle triangle where the right angle, it has to be next to Q? You kind of already told me the answer, but still I want to ask it again. Where should the third point be in this case? Thank you. I wish more people would write note in private messages. Yeah, on the line that passes through Q and is perpendicular to P and Q. Very good. So it's this line now. Very good. You're jumping ahead. I'm very happy to see this. You can put it here or here or here or anywhere that you want on this line and nowhere else. Nowhere else is going to work here. Good. Okay. So I was going to ask you to tell me the general answer now, but you already did. So, oops, that's not what I wanted to do. The third point needs to be anywhere on the line that is incident to Q and perpendicular. I call it perpendicular to the segment between P and Q. So for example, if I put a point, so for Q1, this is the line. For Q2, this is the line. For each Q, I'm going to get a different line. So if I put a point here, it's going to work with Q2, but not with Q1, because it is on the line that belongs to Q2. It's not on the line that belongs to Q1. All right. Why am I asking this? Where are this going? What was our point? Let's recall. What we're trying to do. We're trying to find out how many right angle P participates in, and it's not next to the right angle. So, oops. Doing this, just a second. Here. So let's call it Q is the other n minus 1 points, all the points except P. And L is the set of all lines that we get in this way. For each of the points in Q, we get one line that's relevant to it. And we have L is the set of these n minus 1 lines. Now, as we said, P, Q, R form a right angle triangle if and only if what? Can you tell me this with the word incidence? Can you answer this with the word incidence? PQR form a right angle triangle if and only if. And right angle triangle where Q is next to the right angle, of course. What's the answer? How can I answer this with the word incidence? R is incident to the line of Q. Very good. Very good. Thank you. If and only if R is incident to the line of Q. So for example, here, PQ2R works because R is on the line. PQ1R doesn't work because R is not on the line. That's all. That means that the number of right angle triangles, the answer to our problem is the number of incidences between our points and lines. Every incidence, there's this kind of correspondence. Every incidence corresponds to a right angle triangle and vice versa. So instead of counting right angle triangles, we're counting incidences. Why did this help us? We know how to count incidences. Remember, we had a theorem before by Samurai and Schroeder. That theorem tells us the number of incidences is at most some small constant, number of points to the 2/3, number of lines to the 2/3, which in our case is less than n to the 4/3. So we got, let's say it again, because we turn this into an incidence problem, and we got that the answer is after fixing P, we have at most n to the 4/3 right angle triangles where P is not next to the right angle. Questions? You want me to repeat something? It's yeah, even doesn't matter. Even if you did, the goal here, I guess, is not for you to follow all the technicalities. You can if you want, just to give a vague impression, big picture impression. So we got at most n to the 4/3 right angle triangles are next to one specific P. But I don't want one specific P. I want the whole set, right? We had just a general set of endpoints. We wanted to see how many right angle triangles it can have. So if I don't care about one specific P, I want to say this set has at most X right angle triangles. What can I do? I know the answer for triangles touching one specific point. How do I immediately turn it into an answer? So the total number of right angle triangles that my endpoint set fix is, any thoughts? Anyone? I went too quickly, huh? So even if you didn't quite follow the last couple of slides, what we proved in them was that if you fix a point P, the number of right angle triangles next to P is at most n to the 4/3. Now, I don't have one specific P. I just have a set of endpoints. I want to know what's the maximum number of right angle triangles that these endpoints can have. Do you have any thoughts about how I can give an upper bound for that quantity? Yes, thank you. If every point participates in at most n to the 4/3 triangles, and I have n points, then it's at most n times n to the 4/3. Let me say it slower. They're at most n to the, let's say we take 1 point. They're at most n to the 4/3 points that, n to the 4/3 triangles that use this point. Then we go to the second point. They're at most n to the 4/3 points that use that point. We go to the next point. There are at most n to the 4/3 point triangles that use that point. So we have n times n to the 4/3, which is n to the 7/3. So what did we do? We just proved that if you have n points in the plane, these n points are going to form at most n to the 7/3 right angle triangles, which is a lot smaller than n cubed. It's only 2 and 1/3. So this is an easy example of how to use incidences. You can use them in much more complicated ways. By the way, in case you're curious, the answer to this question is about n squared log n. This question is solved. You can use a slightly different lattice, something that looks more or less like this. You get n to the n squared log n right angle triangles there. And you can add another step to the proof we just saw. You still use incidences, just a bit more work. And you get that this is an upper bound, that no set of endpoints have more right angle triangles than this. So this was just, even if you did, what just happened? Weird, what happened to the background here? Even if you didn't quite listen, this was just an example of how we can use incidences to solve a completely different problem. And this was an easy one. As I said, you can find a different one in my talk on the New York Math Circle YouTube channel. And there are many more complicated ones. So incidences are really useful. They help in a lot of different places. Some of them that first look completely unrelated to geometry. So that's another good reason to study incidences. And I wanted to add a third one, which might seem a bit confusing. Incidence problems help us understand properties of the underlying geometry. What does this sentence say? So when you study incidences, we start by just wanting to count something. It's what we call a combinatorial problem. We just want to count something. But it turns out that you really have to understand the geometry. A lot of times to understand incidence problems, you have to understand the properties of the underlying geometry. You still cannot understand what this means without an example. Originally, I put here an example, and then I figured there's really no way I'm going to manage to do everything. So unfortunately, no time for this example. The last thing I want to do to finish by 2:30 with these incidences is to show you how to prove an incidence result. So here's the big incidence theorem we saw before. Any set of endpoints, and I'll say again, even if you completely lost me with the right angle triangles, we're done with it. You can get back to listening. Any set of endpoints, any set of n lines form at most this number of incidences. Let's prove it. There are several very different proofs of this theorem. I chose one that I think you can understand in less than half an hour now. Let's see. I'm going to use something that's called crossing numbers of graphs. This proof, that's the tool it uses. So let's first see what that is. I'm going to guess that some of you know what graphs are and that some of you don't know. So let's still see what a graph is. There are two main objects in math called the graph, which is a bit confusing. In this one, the graph contains two things. Some things that are called vertices, which we're just imagining as points here. There's a vertex A, vertex B, three other vertices I didn't give a name to. And there are edges. The edge is just a curve that connects two vertices. Here, there's an edge between A and B. It doesn't have to be straight. You can draw it any way you like. Okay, that's a graph. Some vertices, some edges. We usually write a graph like this. So we can call it G, maybe a graph. And it's two sets, a set of vertices, V, and a set of edges, E. For example, here, this graph has 5 vertices. A set of vertices is A, B, C, D, E. That's how we write a set in math using these curly braces. So that's the vertices of the graph. And the set of edges is pairs of vertices. For example, there's an edge between vertex A and vertex B, so AB. There's a vertex between B and C, so a pair BC. Set of vertices, set of edges. Now you can say, great, Adam, but it's such an intuitive object. You just draw points and lines. Why do you need to make it more complicated by introducing these sets? The reason is this. The graph is the sets. The graph is not the drawing. You can draw each graph in infinitely many ways. Here's the same graph, same set of vertices, same set of edges. I drew it in two ways, and both are just equally valid. And there are infinitely many other ways of drawing this graph. You just put a point for each vertex and connect any pair of vertices that have an edge between them. So the graph is really the set of vertices and the set of edges. You can draw it any way you like. Questions so far? Why do we need graphs? Graphs are actually one of the most common objects that are used these days. They model many things. Let's say you want to study a social network. Let's say Facebook. Router, computer, whatever you want. And connect them if they're connected. If you study the brain, you might want to have vertices for neurons and edges for pairs of neurons that are connected. This is a drawing from a paper about robot motion planning that uses graphs. And really, this is one of the most common objects you see today. It's modeling so many things. You can spend years studying it. We just need one thing about it. The crossing number of a graph. What is the crossing number of a graph? So when we draw a graph, we might have some edges crossing it. Let's see. For example, here, these two edges cross, or here, these two edges cross, right? Now, there are different ways of drawing the graph. Out of all these drawings, the crossing number of the graphs is the minimum number of crossings that you need. We write it like this. The crossing number of G is the minimum number of edge crossings that you need when you draw this graph. Let's see. Let's say that this is our graph G. What is the crossing number of G? Can you tell me? 0. Thank you very much. Yes. It's a pleasure to see that you're with me. This graph, you need 0. You can draw it with no edge crossing, so the crossing number is 0. Okay, let's try another example. What's the crossing number of this graph? Okay, I see a lot of 1s. Oh, and a 0. Very interesting. Let's see. So what was the definition? Let's go back. I'm trying to confuse you a bit here. The definition is not about this specific drawing of the graph, but out of all possible ways of drawing this graph, what's the minimum number of crossings I can find? So this drawing has a 1 crossing. Can you draw the same graph with 0 crossings? What do you think? Can someone maybe draw the same graph with 0 crossings? Yes. One way of doing it, perfect, is a triangle with a vertex in the center. I was lazy. I just turned one of the edges to be not straight. Also, another way is just to pass. If you want everything to be straight, you can also move B somewhere around here. That would work. So what's the crossing number of this graph? 0, thank you. Exactly. Okay, last example. How are we on time? Yeah. This graph. This drawing has 5 crossings. I'll give you a moment. You can sketch on a piece of paper if you have. You can sketch on just annotate here if you want. What's the minimum number of crossings? How few crossings can you get? Can you get better than 5? Let's see a suggestion of 2 here. Can you do better than 2? take a moment. I want everyone to take a moment and think about it slowly, and we'll see. Okay, so what do you think? What number do you want to tell me? You think you can do it with 0, 1, 2? Ones. I like your answers. Thank you. 1. You can indeed draw it with 1. Here's my lazy way of drawing it with 1. If you want straight edges, one option is simply take the vertex at the bottom and put it very high up. It'll also work. And it's actually known, you can prove, it's not so hard to prove, that there's no way to draw this with 0 crossings. So the crossing number of this graph is 1. Okay, good. That's all we needed. Now there's a famous lemma, called the crossing lemma, of a graph is as follows. If the graph doesn't have many edges, you can usually draw it without crossings. Depends. If the graph has many edges, at least 4 times the number of vertices, there will always be a lot of crossings. If you have at least 4 times the number of edges, at least large by a factor of 4 from the number of vertices, the number of crossings is at least the number of edges cubed divided by the number of vertices squared. Okay, just an expression. So intuitively what this lemma says is, when you have a lot of edges, you should expect really a lot of crossings. There's no way to avoid it. Okay, let's prove our theorem. What do we want to prove? We want to prove that the number of incidences cannot be large. Why am I talking about crossing number if we're talking about lines, incidences between lines and points? So let's see. We have a set of m points, a set of n lines. Since we're talking about crossings, you probably can guess that we need a graph. Let's build a graph. So instead of points, we're going to take a vertex for each point. Each point gets a vertex in our graph. Very simple. Each point, you can replace it with a vertex. What are the edges? 2 vertices are connected by an edge if they're consecutive along a line. For example, A and B are consecutive along this line, so there's going to be an edge between them here. There's an edge between A and B. Let's take a look at this line, B and E, containing B, E, and F. There's going to be a line between B and E. There's going to an edge between B and E, an edge between E and F. No edge between B and F because they're not consecutive along the line. Only consecutive pairs of points on the line. Okay, you understand what I mean here? Okay, so from points and lines, we got 2 vertices and edges now. We have a graph. All we want to do is see what we can say about the crossing number of this graph. I want to say 2 things about the crossing number of this graph. Any questions, just stop me. Okay, if this is not clear, I'll repeat again how we do the edges or anything else. Okay, so we have n lines. Approximately, how many pairs of intersecting lines do we have in n lines? In the worst case, what's the largest number of pairs of intersecting lines that we can have? Approximately. I don't care about small constants. So we have n lines. How many pairs of intersecting lines can we have? So what's the worst case? How can you describe to me the worst case? What will happen in the worst case? How can I have a very large number of pairs of intersecting lines? So in the worst case, every 2 lines intersect, right? I can just take randomly n lines in the plane. You expect, let's say no 2 are parallel. You expect every 2 lines intersect. So how many pairs of lines do I have? How many pairs of lines can we have? And choose 2. Yes. So even if you're not used to this notation, there are n ways of choosing 1 line, and then n minus 1 ways of choosing the second line. And because there are 2 ways of getting each, they need to divide by 2. Doesn't matter. There's less than n squared over 2 pairs of intersecting line. Does this say anything about the crossing number? every crossing here, we can use this specific drawing of the graph if we want, right? This is a specific, we can keep the points where they are, keep the edges on the lines that they came from. How many edge intersections can I have when I do this? If I do this, how many edge intersections can I have? I just draw the graph the way I got it. Every vertex is where the point was, every edge is where the line was. How many edge intersections can this lead to? So every edge intersection is going to be two lines intersecting, right? To have an edge intersection here, I need the two original lines to intersect. Since at most n squared over 2 pairs of lines intersect, less than n squared over 2 pairs of edges cross. Is that okay? I am a bit worried that I didn't get many answers here. Does that make sense? Let me know if you want me to clarify this more, please. I'm happy to explain this more if this is not clear. It's not even that important. The point is we just, by basic property of how lines behave, we got to the conclusion that you can draw our graph with less than this number of intersections. What other way do we have of getting some information about the crossing number of the graph? Let's say I want to say something else about the crossing number. What tool can we use? You remember what tool we have that we can actually use here? What tool lets us say something about crossing number of a graph? So I said a few minutes ago, there's this crossing lemma, right? We saw this crossing lemma. Remember, let's go a few slides back. Crossing lemma says the number of crossings is always at least number of edges cubed divided by number of vertices squared. So let's apply it. So I'm going to do this quickly because I don't want it to drown in the technicalities here. It's not important. How many vertices do we have? We put a vertex for each point. We have m points. So we had m points. Now we have m vertices. How many edges do we have? To see how many edges we have, let's go line by line. A line that has k points on it. How many edges is it going to lead to in the graph? I have a line with k points on it. How many edges does it create in the graph? Let's start slower. Let's look at this specific line. It contains A and B. It contains 2 points. How many edges did it contribute to the graph? Good, thank you. Indeed. So it only contributed, this line, the only edge it added to the graph was AB, the edge between A and B, right? It had 2 points. 2 points led to 1 edge. What about this one? This line contains 3 points, B, E, and F. How many edges did it create in the graph? 2, very good. It created the edge BE and the edge EF. Very nice, thank you. So in general, it's not 100% true, but in general, a line that is incident to k points will give us how many edges? See, someone already wrote the answer. Very good. Yes, very good. So it's always 1 less than the number of points, k minus 1. There's an exception, doesn't matter. So if we sum this up over all the edges, we get that the number of edges in the graph is the number of incidences. This is a formal way of writing the number of incidences between P and L. The number of incidences between the points of P, the lines of L. It's just that each line, it's the number of incidences on the line minus 1. You sum the number of incidences on all lines, you get a total number of incidences. Minus 1 for each line, it's minus 7. Doesn't matter. You know what? Even if you didn't follow this, it doesn't matter. The important thing is the number of crossings, the crossing number is at least the number of edges cubed, which has the number of incidences in it, divided by the number of vertices squared. And I claim that this is the end of the proof. we got a bound on the number of incidences. And you might complain, what are you talking about, Adam? We just defined a graph and looked at its crossing number. How did we get an upper bound on the number of incidences? Very simple now. What did we do? First, we said, oh, the crossing number is it's less than n squared over 2 by a basic property of lines. Then we applied the crossing lemma and we got that the crossing number is at least this. Put them both together, right? The crossing number is at least this, at most this. Now throw away the middle, we don't care. We know that the red part on the left is smaller than the green part on the right. The crossing number no longer matters, forget about it. You just have an inequality. I rearrange it. How do I rearrange it? The slow standard way. Multiply both sides by m squared to move m squared to the green side. Divide by c to move the c to the green side, etc. Eventually you get this. What is this? The number of incidences is at most n to the 2/3, m to the 2/3 with some constant plus something I'm not going to talk about, it doesn't matter. That's it. That's the end of the proof. We got the equation. The number of incidences is at most n to the 2/3, m to the 2/3. How did that happen? What this might seem a bit confusing. We actually used a common technique. Let's look at it again. Big picture. What's the big picture? We defined the graph. We counted the crossing number in two different ways. Got an upper bound on the crossing number and a lower bound for the crossing number. Combined both bounds and got the answer. This is a common mathematical tool called double counting. Briefly, this tool would be, you want to solve a problem about object X. You define some unrelated object Y, in this case, the crossing number. You count this number Y in two different ways, combine the bounds, Y goes away, and you get a bound for X. That's what we did here. We introduced the crossing number of the graph, counted it in two ways, got a bound of the number of incidences. Again, if you look at the video of my talk from last year, on the YouTube channel of the Math Circle, you see a very different proof for a very different problem where we double counted something else and got another result. It's a very elegant tool, but it's hard to use because you somehow need to know what to double count. There are infinitely many objects you can define. You need to know what the right object that you need to define and count in two different ways. Like here, how are you supposed to know that the crossing number of a graph is the right thing to count? It's not easy to come up with. Okay, last slide about incidences. So I told you before, this incidence result is really one of the almost the only incidence problem that is solved. Here's an example of a problem that's open. What is the maximum number of incidences between n points and n circles of radius 1? All the circles have radius 1, very simple circles. We don't know. The best upper bound is the same as for lines, 4/3. The best lower bound is this expression that might look weird. This is basically very, very close to n. This is, let me write it here, smaller than n to the power of 0.000001. It's very, sorry, not 0, 1.000. This is very close to 1. So there's still a big gap between 1, n to the 1, and n to the 4/3. This is a very important problem. A lot of it implies a lot of other results in multiple mathematical fields. I assure you, many top mathematicians in the world thought about it for decades. The last progress was made in 1984. Very difficult problem. So very silly, very easy to understand, right? Endpoints and circles of radius 1, what's the maximum number of incidences you can have? Doesn't take too much to understand what it's talking about. Extremely difficult. Like the person who solves it will get a lot of awards, etc. Okay, so that was the end of the part where I talk about technical stuff. Now the question is, do we want to keep going immediately, or should we have like a 2-minute break for people to recover from all these incidences? Anybody wants to say something about it? I support a 2-minute break just for everyone can recover from that part, and then we talk some more. Comment?
Okay. Yeah, let's take a break.
Okay, I'm gonna mute myself for 2 minutes and then I'll be back, and I'm gonna tell you about something else brief for a few minutes actually, but a bit very different. All right, I measured 2 minutes. Shall we continue?
Yes, let's do.
Okay, let's continue. So now we're gonna do, we can talk about whatever you want. You can ask me a question about any topic that you wish, but I thought before that, I wanna spend, let's call it 3-4 minutes about something different briefly. So another thing that I do is I'm a part of a group of mathematicians who like to mentor a lot of research projects. So for example, at all sorts of levels. For example, every summer we bring a group of college students from around the country to spend the summer in New York and work very intensely on research, and they produce a lot of paper. Another thing, I run an online summer research program for people from anywhere in the world, but only people who already studied college level proofs, and they work in big groups and they prove mathematical results together. And we do a lot of other things. And I thought in this program, it might be worth mentioning that we also sometimes work with high school students. So what do? This is quite different because it takes more than a summer. I would say that a project like this on average takes close to a year. The goal is to publish a new mathematical result, and we often succeed. It's not prove a new result, obviously not some groundbreaking or long-standing open problem, but a serious new result that's published in a real math journal. And the way this works is that, sorry, I lost my chat. The way this works is the student works closely with a mentor. It's the professor who's an active researcher and has mentoring experience. And at first, It takes a few months. Usually the student needs just to read stuff. So there's still meetings, obviously meetings to discuss things that are hard for the student to read, that the student might have a hard time with, providing tuition, stuff like that. Then after a few months, usually the student is ready to start working on a research problem. So the mentor would choose some open problem from the field of expertise. That's actually the hardest job of the mentor. You want to somehow choose a problem. On the one hand, you feel like there's a reasonable chance that you solve it. You can solve in a few months. And on the other hand, it's not a completely silly problem. It would still be interesting to people and can get published in a real journal. And then there's regular meetings, meeting regularly, working between meetings, etc. So we do some of those projects. And I want to also convince you not to do this. I guess this is not for most people. For most people, it's really not a good idea to do this. Why? So first, this is not just one more extracurricular activity. It's hard. It's time and mostly energy consuming, because doing math research is hard. For all this time, you have no idea if you just need a few more days to solve the problem, or a few more months. Maybe the problem is not solvable. Nobody can solve it. You're stuck with stuff that you have no idea how to approach. It's hard work, and it can be frustrating. And it takes mostly mental energy, because you have to force yourself to sit down and think about it and try things. And if you just have if it's just one of many, many extracurricular activities, you might not have a lot of energy to do that. It's helpful mostly for people who are specifically thinking of doing more advanced math, being math majors in college mainly. Obviously, it's an impressive thing to publish new research as a high school student. It's not a common thing, and it opens a lot of doors. It helps you get accepted to a top math department for college. Even after you get accepted, it opens up doors afterwards. Let's say you want to go to a prestigious math program that's very hard to get into, it can help. Other things like that. Again, this is really not for most people. If you think that you want to get frustrated and work hard and struggle with this, you can email me. It's very easy to find my email if you Google my name. I guess you can ask also the math circle, and even there are a few people in this audience that I already worked with before and can tell you how to reach me. Actually, the context of this talk, we had a surprisingly nice result with someone here. We managed to improve the best known constant for incidences with lines and points. We still don't know what's the maximum constant that you can get, only the asymptotic dependency. It's a nice, very nice result. They got a better constant that was known. The problem is still open, but a bit less. Okay. So this is the end of these slides. Let me stop sharing. Now let's talk about whatever you want. I'm like, it can be about incidences, about this, about something completely different. What do you want to ask about, talk about? You tell me. Oh, someone asked me if you can have my email in the chat. Sure, why not? So here's one of my email addresses. If you want, you can write. Oops, I wrote it back in personal message to the person who asked. Just a second. Here's my email address in the chat. Okay. Yeah. What? Want to talk about anything?
Something which I always wonder about in mathematics is, how can this be applied somewhere?
Right. Where is this useful? So, so I'm assuming you're asking in the context of the incidences that we just saw, right?
Yes.
Okay. So I try to give some reasons about it, and I would say that incidences are very useful for other theoretical purposes. It's a bit silly to say, but a lot of other mathematical fields, you want to make progress in number theory, harmonic analysis, or even theoretical computer science, a lot of times you do this progress with incidences. So in some sense, this is a tool to help improve other theoretical things. That might not be a very satisfying answer. So it's kind of 2 steps away from getting to the practice. Hopefully then, let's talk about that. Okay, so maybe a silly example would be, so for example, okay, so in theoretical computer science, there's a lot of study of something called pseudo-randomness. So there's a big question: if you had a computer that has access to completely random objects, is it better? Can it solve problems that a computer without access to random objects cannot solve? Or can it solve them faster than such a computer? It's a big problem. And one of the ways people handle this is they try to get a computer to produce something that looks almost random, something that's not exactly random, but it's very hard to distinguish between that and something completely random. Or alternatively, to start with what we call a few random bits, just a few random objects, and amplify this to have an input that looks random that's a lot larger. So for example, this kind of incidence problem, incidences between points and lines, were used in this purpose, for this purpose, to studying pseudo-randomness like that. I can give a lot of examples. For example, what is number theory? So we study integers, right? We have prime numbers, sums and products and numbers, etc. This existed for over 2,000 years, and everyone always assumed that it's a completely useless thing to do. Why would you want to study properties of prime numbers? And mathematicians still insisted, and now all of our cryptography is based on that. When you now pay with your credit card to buy something on Amazon, this uses properties of prime numbers that mathematicians studied before. And again, you can use incidences to get better results for all sorts of things in number theory. I hope that this is at least partially a reasonable answer.
That's really interesting. Thank you.
If you are more now, if you find that you like to work on things that are directly related to the real world, maybe you don't want to go to pure math. There's applied math, there's computer science, other sciences. Some people say that they don't like to work hard on research where they don't immediately see how it affects something. Then this is not for them. More questions? Yeah, you don't even have to raise your hand. I don't mind. You can just either write it in the chat or just say it with your microphone, whatever you want. No, I'm not a very formal person.
Okay, so I guess you're talking about research before. What I guess what are the primary like fields that people would do research in, and what are areas of math that would be like very, very difficult, I guess?
Are you talking about research for students or just research in general for like let's call it senior mathematicians?
Actually maybe, well, actually I guess a better question would be, what research have you done before?
So yeah, so I focus in okay, so if I had to describe what I do all sorts of things. I focus in combinatorics, and in some sense my focus is something that's called polynomial methods. It's a relatively recent technique that started about a decade ago, where you use tools from something that's called algebraic geometry. It's an advanced field. I don't think I ever met someone who studied it before late college, at least. I use tools from that to solve problems in combinatorics. So the problems can be easy to describe, just like the problems that we saw today. But to solve them, you use some more advanced tools, and that's really something I couldn't have talked probably properly on today, because it requires knowing some more advanced math. When we do research with students, undergraduate students, high school students, then we choose specifically topics that don't require too much background. So fields like algebraic geometry require a lot of background. There's no way we can do a proper project there, without studying things for a long time first. So we choose problems in combinatorics that relatively require a little background, or number theory. Number theory also contains some problems that require little background, and you can start working only after reading for a few months. Yeah, and I'm not sure if that's exactly what you're asking, but you have a lot of, there's a very wide range of mathematical fields where there's research in, but you don't get to see most of those, I guess, before college. Only then you start to see, like, I don't know, maybe you heard names of fields of like harmonic analysis, complex analysis, representation theory, model theory, I don't know. But there are a lot of fields where people work on. It's just a lot of them are hard to get into before you know a lot more math. Maybe if I didn't quite answer your question, just let me know what you would like to hear more, and I'll try to answer more.
Are there any more questions?
Yeah, I have one question. Back on the topic of research, is there any student research programs that you would recommend people going into if they want to pursue research as a career choice?
Yeah, so I mean, first, that's what graduate school is for. Graduate school, you learn how to do research, and you do your first research, you have a professor who's your advisor, etc. These days, it's becoming gradually more and more common in math. It's for some people to do research already in college, which is, I also mentor a lot of these projects, as I mentioned. And so there are summer projects for this. Sometimes you just find a professor in your own the college that you're at, and they agree to work with you also. And then even less than that, there's some college, there's some high school research. There's a lot less, but it still exists. So as I said, we do this. I can refer you to other programs who do this also. There are already a lot of undergraduate programs. Undergraduate, there are only a few. Sorry, high school. Sorry, there are a lot of undergraduate programs. High school, there are only a few. For example, in MIT, there's a program where high school students do research. But I think their research, I don't know this program well enough. I think a lot of the research is to reprove something that's already known, but sometimes they also do new results. And you can find spread around the country some more people who do that. Some math circles even have someone who sometimes work with students to do research, but again, it's not that common yet. If you want, I can send you links, but yeah. When you get to college, if you're a math major, then you're in a department that cares about its students, then they'll show you a lot of opportunities of summer programs and other programs that you can pursue. As I said, I run 2 such programs. Usually it's like you get to spend the summer somewhere else. So like, I'm guessing you're already from the New York area, but people from other parts of the country come to spend the summer in New York to do research here. So it's kind of also a nice experience in that direction. Is that what did I answer your question, or did you want to ask more to know something else about it? Oh, someone.
No, that was good.
Okay, let's see.
Thank
What type of mathematics? I get some messages here. What's the message? What's the question? Sorry, I got an issue with my chat. It's best if you write your message as publicly and not as a private message, but you can. What type of mathematics you study if you're going to finance, and how long would you study it for? Okay, so again, there's no one answer here. Depends exactly what you want to do. So okay, so you want to study mathematical finance. So there are a lot of different things in mathematical finance. You can go to less mathematical sides of it or to more mathematical sides of it. And the mathematical field that considered, even though this is not what I do, by chance I know this because the college I work in is maybe the thing it's most well known for is mathematical finance. We have some fancy names there. And the thing they use the most is probability, the mathematical field of probability. This, of course, falls, you have pure probability and you have a more applied probability, and that falls obviously, that falls more, okay, so math you can roughly split into pure math and applied math. It's not completely correct, but let's say to make it keep things simple. And it sounds like you're going more in the direction of applied math. Maybe you want to major in applied math or in mathematics.
What about like quant finance? Like
what about what, sorry?
Quant finance.
Right. So this would fall either under applied math or under financial math major in college. Usually, I mean, there's so many universities, and you can always find some universities that work a bit different. But in general, that's how it works. Yeah, and for that, you don't even necessarily have to go to research. You can if you want to. We have, so in our department, we have someone who used to be a very fancy person in some Wall Street company and made a lot of millions, and then decided he wants to get back to research. So then he got back to be a professor. And he has some special position that he only teaches mathematical finance, and he does a lot of research. So some people like that. But you don't have to have research to go in such a direction. And again, we're talking about you're still in school, right? We're talking about a very early stage. When you get to college, you go to an appropriate program, then part of the job of that program is to tell you how you get a good job in that field. What might be good opportunities for that to do, for you to do. So if people in pure math like to do research programs in the summer, people in more financial mathematics might want to do more like an internship in a finance company of some sort. That's more common. You can still do research, but I think it's considered less common, and I know less about it. I'm not exactly the person to ask about such things. If you have very specific question, I can always refer you to someone who is an expert on these things or runs financial mathematics in some college or something like that.
Thank you.
More questions, comments? Want to yell at me about something I said? Want to share a limerick? Anything?
Oh, okay. So I'd like to thank Professor Sheffer for his time and for giving us such an entertaining talk, and also giving advice to a number of you on future directions. We're always very happy to see him give talks at Math Circle, and we hope to see him again soon. So thank you again.
Thank you so much. And I'm as I said, if I can help with anything, Even if you have more questions about something unrelated to what we talked about today, you're welcome to write to me. Okay. Worst case, I'll tell you I cannot help. I don't know how to help with that. You're all, if I can help with something, I'm here. So thank you, everyone.
Thanks a lot.
Thank you for your time.
Thank you.
Bye.